Okay, so we left off with going through the basics of groundwater. So hopefully you've watched the first video. You know something about porosity and permeability and aquifers and aquicludes and what makes a good aquifer and how the kind of hydrologic cycle works. So we want to focus in this class on kind of disasters and hazards. So although there's not a lot of disasters like that are catastrophic, like let's say some volcanic or earthquake hazards, some can be pretty important to us that we're going to cover really quickly here. So one of the big problems that we get into is with altering the shape of or lowering the groundwater table. And so a lot of times when we pump, we depress the water table around the well. And in some cases it's not a big deal because either we're not pumping that much or the groundwater, it flows really easily, so it doesn't really get affected by us pumping. But, you know, in this little story here, an idea would be if I had a couple wells here and everybody's happy because everyone's pulling from the same formation here. So the water here is shared. So what you do on the left and the right is, you know, affecting each other. If someone built or drilled a really steep well here and pumped really heavily, they could draw down the water table. And it gets to this, because it's a three-dimensional feature, it's a cone. So it's called a cone of depression. And this depression forms around pumping wells. Now, like I said, there's factors that control how much of a depression you get. If the air is super permeable, which means the water can flow super easily, then you don't get as much of a depression. And of course your pumping rate and things like that. But when we pump a lot of water from the ground, there's no doubt that we depress the water table, but we depress it right around the well significantly, forming this cone of depression. And when we do that, we can impact other wells. And so we get this problem of just in general where we're pumping too much water, we're affecting our neighbors or our neighbors' farms. And this has happened in California. And when you watch the little video clip, it'll talk a little bit about that. So one of the big problems, of course, is contamination, and that can be from a variety of things. But our issue, of course, is that any fluids, just like water, can penetrate into the material, move through those open spaces, and get into the groundwater. And so that can be landfills or leaking septic tanks or spraying pesticides or, you know, using fertilizer on crops. All these things can be mobile when we get rain or things like that. And it can move that material down into the groundwater. And then once it hits the groundwater, it's going to flow in the direction the groundwater is moving. And so then it can eventually make its way to populated areas. And then we have issues with that for sure. So septic tanks we talk about are places that we can have leaks and things like that. Landfills that aren't properly designed, we can get leaks that happen from those things. And so contamination, like I said, can come from a variety of sources. The issue is that it gets to the table and water table and then it starts to move. And so just to talk about, you know, a little bit of both what we talked about before is the idea of something like this, where if you're smart human because you took this class and you said, I have this lovely piece of property with my house, I'm going to put a little septic system in, and of course I need drinking water. And you knew that the slope of the land was kind of sloping from about where your house is down to the left, and you remembered from class that means that the water table is probably doing that. So it's higher under your house and it's sloping away. So that means that's the direction that the water in the ground is moving. And so I'm going to put my septic tank downslope from my house just in case it leaks. If it got into the groundwater, it would move away from my well because I'm putting my well up here on the top of the hill. And you're pretty smart and everybody's happy. But then if someone came over here and decided they wanted to do some pumping and they put a well in and they pumped a lot of water, they're going to depress the water table. And remember, it goes from high to low. Here it can go this way, but now that I've changed the shape of the groundwater table, now my septic tank ickiness can potentially flow towards your well. This is not a good story, right? So changing the shape of the groundwater table by over pumping, if it's local or over a large area, can change the direction of the water flow. And of course, if it's related to pollution, Now I'm moving the pollution around in different directions. So definitely an issue for pollutants like that. In other cases, we have what's called saltwater intrusion. So places at the coastline or islands, they have water that is in the material here, the sediment or the rock. But over the oceans, it's salt water that's seeping into the ground and filling up the open spaces. But over the land surface, it's fresh water. So there's a boundary here between fresh water and salt water. Basically, there's a bubble of fresh water sitting here. But if I pump too much, I depress this table here, and I potentially can pull in some salt water. And so if you live at the coast or you're an island, you really have to manage your pumping so that you don't pull in some salt water, because once you do, you can't get it out, and that well has to be abandoned. And so there's issues with that have to be taken into account depending on where you live. Some of the more dramatic ones, and we're going to spend more time next week talking more specifically about sinkholes, subsidence, and that kind of stuff. But of course, because we're talking about groundwater, because groundwater is one of the causes of sinkholes and subsidence, but not the only. So we're going to talk about them a little bit here and then more in the next chapter. But the idea that we can have a collapse feature related to groundwater is usually where we have the rock called a limestone in the subsurface. And the reason that that's true is the limestone can dissolve over long periods of time as the groundwater is flowing through the rock. Limestone tends to be highly fractured, and so as water falls on the surface and percolates down to the rock, it follows the fracture patterns. That's where the porosity and permeability is. And as it moves along there, it starts to widen and open those. And so we get a lot of caverns. And so most of the caverns, like if you've been to Karchner Cavern or Carlsbad Caverns, a lot of those features are there because of limestone is the bedrock that's there. And groundwater over, like we're talking a long time, hundreds of thousands of years, millions of years, the water moving in there has dissolved some of that calcium carbonate, which makes up limestone, and created these caverns. Well, if there's a cavern that's close to the surface here, we wouldn't know it if we're living on top here, and over time those things can collapse. Either we have a water table that's really high and it's filling the cavern with water. If that's the case, the water is a good supporter, and so we don't really have a problem with that. But then if we have a huge community and we pump the crap out of our water table and lower it, and it gets below the cavern, now there's just air in here and it's not as supportive as the water. And so we can get the weight of all the structures here causing a collapse. And so we can get these depressions that occur. They can be fairly quickly occurring events, or they could be a slow sinking event. But definitely a problem, but typically because of the type of rock that exists there. That's why here in Arizona, we don't have a big problem, at least in the valley, because there's not a lot of carbonate rocks or limestones. Back east and other places where there's lots of limestones, it is a big problem. Another issue we have is this settling or lowering of the land surface, which is what we're calling subsidence. And so we see that in certain places. One place we see it a lot is near coastal communities. But the idea is that the sediment that we have, we said water percolates through the open spaces. And so it fills them up. And then we have that water table boundary between the full spaces and the not full spaces. And it's the same thing with the caverns. If I put a lot of weight on top, so I build my community on this material, it can't really crush down, compact the sediment because there's water in between. And we can't crush it because the water is holding that open space open. But if I pump it out and I don't replenish it fast enough, then that open space, which is now just air, can crush and collapse. And even though the spaces are super tiny, there's billions and billions and billions of them in the subsurface. And if I lower the water table enough, all those little spaces that crush down can cause the elevation of the surface, the land surface, to lower. And so that is subsidence. And of course, if you're near the coast and you're not much far above sea level and you have this compaction based on withdrawal of groundwater, that's a problem, right? So we get some issues with that. And so coastal communities have big problems with that. Places where we have deltas. And so, of course, if we go to Mississippi and we look at New Orleans, it's a huge problem there. And it's huge because the material here is all sediment. It's all built from sediment. And so we're going to live here. We're pumping out groundwater. We're causing the land surface to subside there. It is not a good thing for New Orleans because, of course, they are below sea level already. And so what's happened over, time as the Mississippi rivers come out and dump sediment in this whole area over thousands of years and grown this part of the country, actually. But as it moves around and it stops supplying areas, it sinks, and then we come in, of course, and we pump water out, and that causes the ground to sink. Pulling oil out, that causes the ground to sink. That's another problem. If we were to look at a cross-section, you can see that this is the Mississippi River's up here, elevation. This is a lake. Oh, here's New Orleans. It is below sea level. So this is all sinking for a variety of reasons, but certainly one of those is that we're pulling water out and causing the sediment to compact. And that's happened in the valley here. It's also big in the San Joaquin Valley in California. Some of the largest kind of compaction subsidence rates are seen in this area because it's a huge growing area and they use lots of groundwater for that. And so this sign here is just a typical picture, but in 1925 it's arguing this is where the elevation of the land surface was. And in 1977 it was here. So it's dropped at least 50 feet in those almost 50 years, so like a foot a year. So it's crazy the amount of, now of course this is a huge farming area, so there's not a lot of structures here. So you'd think that that would be a problem, and it is, but there's not huge, cities in these areas where they have the highest rates because that's where they're growing everything. Now look, here in the valley, we get same thing. We get subsidence. But because we don't have as big an area as California and we're not pumping as much groundwater, we don't get the whole area sinking, though we do in places that it's not as severe. We get what are called earth fissures. And what that is the differential settling of the land surface based on some areas compacting more than others. So earth fissures tend to show up near mountain fronts, and that's because the sediment isn't as thick near the mountain, but thicker in the basin. And our basins and mountains are here because of faulting. And so we have a thick sediment here and not as thick here. When I lower the groundwater, I get compaction. But here can compact a lot. Here can't compact much at all. And the different compaction rates cause these big fissures to show up. And that can definitely be a problem. And so if you have structures and things across here, then of course those can be impacted by that. And so this high-tech little diagram is showing that it's not always near mountain fronts. Remember, we're a valley that's filled with sediment. The sediment is covering the bedrock, and we don't know what it looks like down there. It's not just flat and perfect everywhere. So in places where we have a topographic high in the bedrock, means that the thickness of the sediment is different in different parts of the valley. And so the groundwater is filling up everything. We have this kind of level here, and it's mimicking the land surface. The same problem occurs as I pull water out and I get compaction. This can't compact as much as this, and I get these fractures that occur in these areas. So this is another problem, and of course it's not just Arizona, but because of the nature of our geology, we get these earth fissures. Once again, we'll talk more about this in the next week's module, where we talk about subsidence, sinkholes, and earth fissures. But usually, earth fissures here are related to groundwater withdrawal. And so some of the problems we talk about with groundwater are pollution is a big problem, of course. Then we have these compaction problems, so subsidence. We have sinkholes and things like that. So those are the things we kind of look at. And so how do we kind of resolve some of those issues? The idea of mapping the groundwater table, so I know direction of flow, can definitely help me figure out where the pollution is coming from. So in the lab, we're going to have you try to play around a little with that, give you some maps, kind of figure out direction of flow, and you can use that to figure out who's the polluting, and it can give me an idea of how long it'll take for the pollution to get from one place to another, because I can determine the rate at which the water is flowing. If I have enough wells, I can be like, oh, hey, I found some pollution in this well, and that well is 5 miles from your house or the city or wherever there's a populated area, and it just showed up in my well. So it is moving, because I can do some calculations on its permeability and the slope of the water table. Maybe it's moving a mile a year, so I have 5 years to figure out how to stop it. And a lot of times how we do that is we drill wells and pull the material out, but I got to be in front of the pollution. If I pull it from behind, then stuff escapes. So this is why I have to know its rate. If I'm going to put in some wells to pump the pollution out, I have to be ahead of the plume. And so knowing the direction it's going and its speed can help me do that. Okay, so some things that were enacted, designed to help with some of this groundwater problem are listed here. So I'm going to let you read through some of these really quickly just to give you an idea of how the government has attempted to regulate some of the issues with groundwater so that we can tackle some of the pollution problems here. So you can read through those. Most of those are related to saying we need quality drinking water, and that if there is some type of pollution, who's responsible and how it will be cleaned up, and government agencies that would, enact and take care of some of those things. How we can kind of fix some of the problems is with these synthetic liners or membranes. When you build a landfill done properly, you need to line it with materials that don't allow water and liquids to penetrate so it can't get into the ground. So definitely in areas that potentially could have some contaminants need to be sealed properly, so we could do stuff like that. Occasionally, if we see that there's pollution and it's moving in a certain direction, we can actually physically try to stop it by digging down and putting some material that would keep the water from moving in that direction. Sometimes we just take out the material and clean it, but the idea of a physical containment would be something like this, where here's the surface, I have some source material sinking down, and so I'm going to build a wall here that's actually going to stop it from moving through, or actually treat it. It's going to move through this filter and be treated on the other side, but something that's physically going to stop it, we could do that. Or we could fill it with material that would, kind of seal it off. We said if we enclose the open spaces, it's not permeable, the water can't move through there. So that's a way that we can stop the material from moving. If we know the direction, we know where to seal it, and we can kind of surround it or keep it from moving, and then we can isolate it, and then we can sit there and figure out how to treat it. Or we could just leave it. Do we actually have to pull it out or not? But a lot of the methods that we do are some form of what's called pump and treat. And this is the idea that we know the direction, remember, and we know how fast it's going, so I can drill wells to pull water out and then treat it in some fashion. And that can be treated in a variety of ways. It can be filters. It can be stuff where we use different what's called air stripping, where we use different air to push through and get some out. Sometimes we burn them out, right? So we can incinerate some of the volatiles that are in the groundwater. We pull it out. Sometimes we use bioremediation, some type of pump and treat where we have biological organisms that can do that. But the big deal here is that we are finding the plume. So the idea is I have wells. I determine where the contaminant's coming from because I know the flow direction, because I can map the groundwater table, and I know it's flowing from high elevations to low elevations, and I can determine its speed. And so then I get ahead of the plume of pollution, and I design a solution. Am I going to build a wall around it? Am I going to put in recovery wells in front of it? So I drill those in there so I know it's coming this way, and I start pumping. I get the pollution, I get it out, and I treat it in some way, and then I can put it back in the ground, right? So that's the really general way that we would deal with some type of pollution in the ground. And then I just kind of threw this in there. This is from SRP. So now SRP has a lot of wells here in the valley, and so they actually have this little diagram that shows how the well was constructed. It shows the materials that they drilled through when they made the well. It shows where the water table is. It has water quality data. It has different information about how much water it can produce based on its permeability and things like that. And so they're constantly monitoring the water that they pull from the ground. And so it's, even though you might argue that your tap water tastes kind of crappy, it really is at a higher standard than most water you have access to, because it's constantly monitored, right? So they're always testing it. They're always trying to figure out, that these contaminants are not at levels that are not safe for human consumption. They're always kind of monitoring the condition of the well, and they're looking at this pump data to see, how much water it produces and things like that. So the groundwater here is pretty safe, but there certainly has been areas where we've had contamination, and we've used the methods I just talked about to try and treat those by finding the plume, knowing something about groundwater flow, knowing something about the elevation of the water table, knowing something about its speed, and we can use all that to kind of clean up this issues that we have with groundwater. Okay, so next week we'll talk more about the other hazards related to that, the sinkholes, the subsidence, and the earth fissure stuff.